This talk is about root server abuse. It's sort of a follow-on to a talk I gave last year. I'm doing this work with, in conjunction with Kata, and we're still interested in understanding why the root servers are getting slammed so much. And unlike the previous study, where we analyzed traffic, this one is a simulation, a lab simulation of various name servers, caching name servers. So we're interested in seeing, are any particular name server implementations worse than others? Are they more abusive? Are they distributing the load as we would expect them to? And here's a cartoon of the test network that I used. There's basically 5 boxes. One box handles root server queries, one handles top-level domains, and one handles second-level domains, and actually anything beyond that, third level, fourth level, etc. There's a simulated wide area network with packet loss and delays. This guy is the caching name server, where this is the part that we're interested in testing. And there's a box that just submits a whole bunch of queries, as a user might. The workload is taken from web proxy logs, about 12 hours worth. There were 5.5 million total DNS queries with 107,000 unique host names, 70,000 unique second-level domains, 431 top-level domains, many of which are invalid, and only one root. I made up a bunch of zone files, and the contents of those zone files are sort of based on reality. For the root and top-level domains, it uses the actual zone data for the number of name servers, and the TTLs on the name server and glue records. For the second-level domains, since there were so many of them, it's impossible to have the actual values there. So I took a sample of real data and then used that sample to generate random values. Again, here trying to mimic the number of address records per name and the TTLs on address, name server, and CNAME records. One thing that's a little different than reality is each second-level domain has just 2 name servers, and this last measurement, this 35% probability that any name is a CNAME record, was actually based on actual measurements as well. Here's a sample zone file. I don't expect you to be able to read this, at least not on the screens. If you're really interested, you can look at the slides. But this shows some samples from my simulated.org zone. This is before the move to the Anycast servers. So there was something like 8 or 9 different name servers. And on the right side, you see some sample zones, some second-level zones under there. This is a list of the caching software that I tested. 2 versions of Bind 8 and Bind 9, DJB DNS, and 2 versions of Windows. These different software packages run only on the caching name server box. The top-level domain, second-level, and the roots all run Bind 8. I did 6 different test configurations. The simplest one has no delays and no packet loss. Then I did one with constant 100 millisecond delays and no packet loss. I have 3 with linear delays, which I'll explain in the next slide what that's about. 1 with no packet loss, 5% packet loss, and 25% packet loss. And finally, 1 with 100% packet loss. Here's how the linear delays were configured. On the first name server, it was 40 milliseconds delay and increased by 10 milliseconds for every name server after that. So the 13th name server, in cases where there were 13 name servers, had 160 millisecond delays. So here's a few results. This graph shows total number of queries sent by each tested configuration, each version of the software for the case of no delays and no packet loss. The blue represents queries sent to the roots. The green is queries sent to the top-level domains, and the red is queries to the second-level domain name servers. And you can see that bind 8 has the most queries with just over 1 million total for this 12-hour period. And then they sort of go down from there. One of the things that's sort of striking about this is bind 9 sends quite a bit more queries to the roots than any of the others, although DJB DNS is similar. And there's a few numbers down there just to show you, just to give you an idea. And here's another result of a sort of a more realistic case with linear base delays and 5% packet loss. And the numbers are about the same. In most cases, they just went up a little bit due to the delays and the loss. So bind 8 sends a lot of queries, and here are some of the reasons why. At least in my test where I had IPv6 on the box, it sends both quad A and A6 queries to all of the name servers, the roots, the second level and top level domains, for any name server address that has expired. And bind 8 and actually all of the other software except for bind 9 do what I call they forward cache misses for pending hits, or they forward misses for repeated queries. And here's sort of an example of that, a TCP dump output where there's 2 queries right in a row for the same name, and if you spent the time to follow this through, you would see that the bind 9 caching name server sends 4 queries all the way through the roots, the second level domains, until it gets the first answer back. So in the case where you have a high rate of queries for a single a name, you can get a lot of queries, perhaps an unnecessary amount of queries. Bind 9 is the only software that is sort of smart enough to realize that it's expecting a reply for this name any second now, and it postpones later queries until that reply comes back. But on the other hand, bind 9 still sends a lot of queries to the roots, and one of the reasons is that it sends A and A6 queries for both expired name server records starting at the root. So when the cached glue record expires, it doesn't start at the top level domain. It starts back at the root, perhaps because it doesn't trust the cached data for the top level domain. And below there's sort of a real world example where this might be excessive. Microsoft is a relatively popular site. They have 4 NS records, 4 glue records with relatively low TTLs. So every time one of those glue records expires, a bind 9 caching name server is going to send 8 queries to the roots. And DJB DNS is similar. It requeries the roots for the expired glue records, but only for one of the name servers. It doesn't query both, unless I suppose the first one doesn't come back. And it only sends IPv4 address queries. One of the things that's unique about this software is that if it gets an additional record in a reply, that is a glue record with an IP address that has a TTL 0, it thinks there's something fishy about that and starts back at the roots to get that name server's IP address. And here's an example of that. The first line shows the user's query. The second line shows shows the caching name server asking for this address at the top level domain. The answer comes back, and there's a glue record with a 0 TTL, which you can't really see. But in the fourth line there, you can see that it goes to the roots for ns0.kujibo.com, and so on. Here's all of the results for bind 8, except for the 100% loss test, which I'll show separately. One of the things that's interesting about this is, as the sort of network conditions get harsher, bind 8 sends slightly fewer queries. I don't know if you can tell, but the graphs go down a little bit, especially for the 100% millisecond or 100 millisecond delays. There's quite a drop to the top level domain queries there. Here's the same thing for bind 9. And one of the things that's interesting to note here is that the number of queries is unaffected by network delays, but only by loss. So for the first 3 cases, the total number of queries is just about the same, just about equal. The results for DJB DNS, nothing really obvious to comment on here. Here's Windows 2000 and Windows 2003. This graph I find particularly interesting, however. This is the tests with 100% packet loss. So this is what happens when a caching name server can send queries out to the roots, but for some reason those responses aren't getting back. And there's quite a lot of difference here between the different software and how they behave. Bind 9 is obviously lower than any others. And remember from the workload slide that this workload has 5 million total DNS queries. So in the case of bind 8, it ends up sending about 38 million queries out to the roots for those 5 million original queries. And obviously Windows 2000 is even worse with something like 65 million. And here's another way of looking at the same data. These are traces of the query rates for all of the different configurations. The black line shows queries generated by the user, and as you can see, all of the software except for bind 9 actually amplifies the query rates. I don't have the data shown here, but due to some other tests that I was running, at a higher query rate, some of the software would actually throttle itself. You can't see that here, but I think Windows 2000 did not, and bind 8 and 9, or DJB DNS and bind 8 actually did throttle themselves at some higher level, say 2,000 queries per second was their limit. I have a little bit of data now on the way that these different caching name servers distributed the load to the roots and one of the top level domains. So the common perception is that the name servers pick the best one based on measurements that they perform. They know the network conditions, they know their round trip times, and so on. Here's an example of how this data looks. There's 2 data sets shown here. The red shows queries sent to the roots, and the green shows queries sent to the .com TLDs. The x-axis has the 13 name servers for each one. And the 2 y-axes show the counts, although that's sort of not critical here. This is for bind 8, and in the case where there's no packet loss and no delays, bind 8 just latches on to one particular name server and keeps using it. There's no reason for it to switch. The rest of this look pretty reasonable. There's something funny going on, however, with the 100% packet loss case where it hits some root servers a little bit harder than others, twice as much it looks like. But for the cases with the linear delays, it looks reasonable, sort of what we would expect. Remember that in all these, the first name server, the A, has the lowest latency, and the M name server has the highest. Here's bind 8. For the no packet loss, no delay case, it's much more even. It's round robin, essentially querying all name servers equally. And the same for the other two cases there at the top. And a nice exponential distribution for all the linear delay cases. DJB DNS always does essentially round robin distribution to the name servers regardless of packet loss or delays. And that's no surprise. They mention that in the software description. This is Windows 2000, and the surprising thing here is for the cases with linear delays, it seems to ignore any actual measurements at all, I guess. It always picks essentially always picks one name server and just sticks with it. And additionally, for the .com name servers, it always ends up picking A and sends all of its queries to that. For the roots, it's a little more random. This may be an artifact of the way my test was set up. I'm not sure, or it may just be that the way Windows 2000 works. For the 100% packet loss case, it's interesting that there's some green lines there which probably shouldn't be there. The x-axis shows just one, so it sent one query to the top-level domains for a few cases, but that's sort of an anomaly. And here's the current version of Windows 2003, and it's a little bit better. Still some funny things going on with the 100% packet loss case, where some root name servers get hit a lot more than others, and in the linear delay cases, it's not quite as smooth, or not quite the distribution I would expect to see, but at least it is distributed a little bit. So now I have to say a few things about this quote is from Slashdot, based on the talk that I gave last year, or the paper that was presented last year, where I mentioned that only 2% of the queries hitting the roots are valid, basically. And here's the punchline from last year's talk. These are the 9 or so categories that I came up with, and I told you that there's a lot of repeats, there was a lot of unknown top-level domains, etc., but the legitimate category only got about 2%. So I took the results from this study, my simulations, and ran it through the software from last year's study, and here are some of those numbers. Unfortunately, I didn't see that all of my queries were legitimate. Not surprisingly, I would expect to see this unknown TLD category, but I was a little bit disappointed to see so many repeated queries show up here. And the referral not cached category has a little bit too high of percentages. So the explanation is that in last year's talk, I was not really aware that software like Bind9 and DJB DNS start over at the roots for certain cases for expired name server records and zero TTL glue records. So if I exclude those queries from the result and run it again, this sort of shows some of the numbers. It's better, but it's still not perfect. Another explanation may be that in last year's study, I assumed that all of the top-level domains and the roots had TTLs longer than the time of the test, so longer than 24 hours. And in running these tests, that's certainly not the case. There certainly are top-level domains with TTLs shorter than 24 hours, but I'm still not sure that it's just as simple as that. So this perhaps means that that number of 2% is higher, and that the case where this referral not cached category, which is about 4%, those may actually have been legitimate queries, and some of the repeated queries may have been legitimate also. So I have just a couple of conclusion slides left here. Bind 8, as we've seen, can sort of latch onto a single name server in a low latency, low loss condition. And unfortunately, I didn't run more tests and find what those thresholds were. There must be some threshold where, you know, it decides something's not quite right and it starts to distribute the load a little bit, but I don't have those numbers. DJB uses uniform distribution in all cases, ignoring TTLs, or ignoring round trip times and packet loss. Windows 2000 DNS server has a really, really bad server selection algorithm as far as I can tell. And the 2003 algorithm is maybe a little bit better, but I think could still be improved. It seems to me that the fact that bind 8 at least and bind 9 also sends queries to the routes for IPv6 addresses may be causing a little bit of abuse. I really love the fact that bind 9 does not forward cache misses for pending hits. I think that's a very nice thing. And another thing I like about bind 9 is that it attenuates the load in the case where it's not communicating well with the root name server. It doesn't send more queries than the user sends, it sends fewer. And finally, as I admitted, I need to improve the models for analyzing traces, real traces from real root servers and so on, to see if we can figure out how many queries are legitimate and how many are bogus. That's it.
Thank you. You didn't go as long as I thought you did. Any questions from the assembled multitude? For Dwayne. Okay, I've got one for you. Are you, as you try and refine your technique, are you going to try and refine your test bed to more accurately reflect deployed DNS infrastructure, or are you going to just work on the modeling and the software? You
mean, for example, not assuming that delays are linear across name servers and so on like that?
Yep.
Yeah, I think that's an important next step. But it's obviously difficult because you know, the round trip time distribution depends on where you are and who you are and that sort of thing, I guess.
Yeah, that's part of it.
Difficult with all the Anycast name servers out there and so on.
That's actually sort of intriguing, because if you actually put an Anycast instance into play in your test bed, it would be part of the problems with managing Anycast instances is how do you actually monitor them and do load sharing among them, or do you just sort of roughly guess and saying, well, that's sort of an underserved area or an underserved thing. We'll put something there because latency is so high, and you hope that things will work, right, based upon routing protocols and the like. So it would be interesting to see how you do your test bed.
Yeah, I don't think I'm nearly to the point where I could actually use actual Anycast servers in the test bed, but certainly it's easy to you know, say change the distribution of TTLs or round trip times.
That'd be interesting.